So there are some power aware design techniques which requires specialized converters. So one is your dynamic voltage scaling, which is quite common in processors, uh, and then dynamic frequency scaling, and if you combine both it becomes DVFS. So DVFS is the most commonly used technique in processors, where what you do depending upon the performance requirement, you increase or decrease the voltage as well as frequency. So when you are running your, let's say, digital circuitries, you know, with the voltage the delay changes. So if you are running your processor at 1 gigahertz, you want to minimize the delay. So you want to operate at a maximum supply, and if let's say you want to run at 1 megahertz, then you don't want the same voltage because now you can afford larger delay. But if you keep the same voltage, then there are some leakages in the circuit that will be more. And you know that your power in any switching circuit is CV square F. So if you reduce the voltage, you get the square factor, and now you reduce the frequency also, so you get a cubic advantage here. And that's why in most of the processor, if your performance reduces, you reduce the clock frequency as well as voltage. Okay, so in dynamic voltage scaling, it's a technique to improve system efficiency by dynamically varying the supply voltage. And supply voltage is reduced when load demand is low, can be used for envelope tracking or compensate for the process and temperature variations in the devices. Okay, so when we say process and temperature variations, so now assume that you have designed your circuit. Mostly you design a typical, okay. So, but when you have to meet the spec, you have to look at the worst case. So you want to run your circuit at, let's say, 1 gigahertz. You want to make sure your timings are met at the slowest corner, which means when you go to the fast corner, your circuit is now over designed. So you'll oversize all your transistors, everything. So you will be burning more current in the circuit. And so what you do basically in the dynamic voltage scaling, you design at a typical corner, and if you have some way to, and I think we talked about this, how you track the PVT, you can have a ring oscillator, and based on that you can. So let's say you are able to track the process and temperature, that will give you the code. Once you have the information at what corner it is fabricated, you can change the supply voltage. So if it is at the fast corner, you can reduce the supply little bit to even to achieve the same delay or same timing. If it's at a slowest corner, you can slightly increase the voltage so that you don't need to oversize your transistors. So that's the advantage here with DBS. So one example of DBS is Class G amplifier. So you would have heard Class H amplifier. Oh, sorry, Class D amplifier. There is a Class H also. Will come to that. And you would have heard Class AB. So in the Class AB, what you have actually, uh, so just like a LDO, you have a dropout voltage. So whatever the dropout voltage, that will be a loss in your circuit. So in the Class AB, you have a dropout voltage, and that dropout voltage means whatever the overdrive you are using across these transistors, it could be MOSFET also. Here it's a bipolar. So that is lost. Okay. So all these are, so this is your VDD. So this is lost. Now if we say, think that depending upon the output or input, I can vary the volt supply of this. So let's assume that your input is varying from 1 volt, 0 to 1 volt. Okay. Or here I am using both, so you can say plus minus 1 volt. Okay. And depending upon, so let's say this is audio amplifier. So depending upon the volume, your input will change. So let's say at the lower volume, my input goes below 500 millivolt or so. Then for when this is 1 volt, you need this supply to be more than 1 volt. Okay. You need some dropout across this, the collector to emitter voltage of this bipolar. So let's say that is 100 millivolt. So which means this should be at least 1.1 volt in order to achieve 1 volt at the output. Now you reduce the volume and your amplitude input or what are required here output is, let's say, below 500 millivolt, which means I can keep this 600 millivolt. So now let's say if I have two supplies, at 1 volt I use this VDDH, at 0.5 volt or below I use VDDF. So 0.5 volt when it goes, if you, let's say you keep using 1.1 volt, the dropout across this transistor is 0.6 volt. But if I switch to this, let's say 600 millivolt, then you have again reduced the dropout to 100 millivolt. So you can reduce the losses in the circuit, so efficiency will be much higher. Now how many supplies you use, it will depend, that will define your average efficiency. Now there is another category which is called class H, and it is used, the concept is used in the envelope tracking of power amplifier in most of your RF transmitters. So now this is your power amplifier and this is your DC-DC converter. If I keep this supply fixed, again all this red portion you see, that is the loss, and this is my signal. See, if I track my supply with the signal like this, and whatever dropout voltage you have defined, it's 100 millivolt, always keep your supply only 100 millivolt higher than your input, which means your supply should be tracking the envelope of your signal. If you can do that, then your losses will be reduced. And you can see a huge advantage actually. Instead of, let's say, you are getting a 50 or 60% there, you can achieve a 80% efficiency in the other case. Okay. So, or in another way, you can think about in terms of LDO. If you keep the dropout voltage fixed, irrespective of your output voltage, then your losses will be fixed. You can always achieve a high efficiency no matter what the voltage is. But if you keep the input supply fixed there, at a lower supply voltage, dropout will increase, your efficiency will drop. So you are doing nothing but regulating the dropout voltage by tracking your dropout with the shape of the signal. That's all you do here. And this is called class H. Okay, this is another version of. So class G is more like a discrete in nature, and you can use more level of supplies if you want. But class H is a continuous. Okay, so then dynamic frequency scaling. The dynamic frequency scaling, what you do, you just change the frequency based on the data actually. So if your data load is higher, you increase the frequency, data load is less, you reduce the frequency. So dynamically keep changing, and overall you can achieve a better system efficiency. And this is how it looks like. So you have a voltage and this is your CPU performance. When you are running at a lower performance, you reduce the voltage. At peak performance, you increase the voltage to the max. And here you see V square F. So this is only, if you change only V, okay, then reduction here compared to if you change V square F, which is CV square F, it's much higher. So adaptively you can change the supply based on the performance. So when your performance is very low, you get a cubic advantage here. So that's why this term is more like non-linear. You can apply the same concept in high-speed serial link also, which are your CDRs, like PLLs and all your clock drivers, IOs, everything. So this is the energy per bit rate, which is the performance, defines the performance. So now you can see here adaptive supply. So when your performance is basically increasing here, what you do actually, energy per bit, if you don't vary the supply, it will be much higher. The efficiency is measured in energy per bit here. Okay. But if you use adaptive supply, you can see here your energy per bit is like much less compared to this one. So think about your DC-DC converter. When you are running at a maximum load, your conduction losses are dominant. But if you keep the frequency same at light load, your switching losses will start dominating and efficiency will be less. So you think from that perspective, you can think this is the loss actually. So at light load, your loss is much higher if you don't change the frequency. But here, we are changing both frequency and supply. So you try to maintain the efficiency of the system or loss of the system at the minimum possible. This is the thing they use like a multiple and based on the I think it's nothing but the muxing and they try to change the number of these parallel basically transmitter they are using. So normalized power here again multiplexing factor they change. So multiplexing factor they increase when they are operating at a higher load and when the load changes reduces they reduce the multiplexing factor. So it's just like you can say they are using multiple phases just like we saw in the LDO and you keep basically turning off the phases as your load reduces. So they are using the similar concept. Okay, then how do you generate that supply? So one simple concept here shown in this. So if your that VDD is generated from DC-DC converter, what you can do, you can have a VCO in the feedback and have a reference clock. So reference clock, let's say you have a 1 gigahertz, then you want the frequency of this VCO to be 1 gigahertz. So your buck converter will force this control voltage, which is your supply, in such a manner that this frequency is 1 gigahertz. Okay. So and VCO, the reason we are using VCO because your delays are measured in terms of inverters actually. So this VCO if is implemented using a ring oscillator, which is nothing but the cascaded inverters, then it will represent your digital circuitry, whatever logic gates and everything. So if you can run this at a lower voltage, you can run the other circuitry also at the same voltage. So it will now if your process is changing, let's say it went to at a slower corner, then this frequency will automatically go down and this loop will force this voltage to go high so that it is again locked at 1 gigahertz. So dropout voltage depending upon how you design it. If you can sustain 50 millivolt, then have a 50 millivolt. Usually this is the I have shown a PMOS, but these amplifiers have a both N and P, push and pull. Okay, so it will have a source and sink both. Okay, so you have to regulate the voltage of both. It's not only one, but if you want to let's say only one side, on the one side, whatever the minimum voltage it goes, you always keep your supply 100 millivolt higher than that. So what you will do actually, your reference will become your signal plus 100 millivolt. So your Vref is that, then it will always regulate your output to Vin plus 100 millivolt. That's what you have to do. And if you have a both side like this, then you may want to regulate. So you have a positive VDD plus VDD and minus VDD both. Then you have to regulate both and then you will have a separate regulator obviously for both of them. Single inductor. CMOS. So if I want to generate two outputs from here, with a single inductor, so what I can do, which is SP. This and call it S1. So they are isolated outputs, so they should have their own capacitor, so they will have their own load. This is VO1, this is VO2. So let's say this is your controller. When I say controller, it has a compensator and PWM, everything inside. So you will directly get PWM. Sorry, this is 2. PWM. Then what do I need to have? I need to have some logic here, because I have a single power stage here, one inductor. So I cannot feed 2 PWM in one. So I need to have some logic here. This will generate your PWM. And this logic is nothing. I mean, can somebody assume what should be this logic? So let's say, what could be the, so we are sharing the same inductor, which means we can share in time multiplexing. Okay. So for one cycle, let's say I am feeding one duty cycle, for another cycle I am feeding another duty cycle. Correct. So let's say this is VPWM1. This is VPWM2. So the VPWM, I want to have something like this. Okay, and you keep repeating this. So let's say my inductor current is DC. Your inductor current will be doing something like this. Okay, what is the average current? I load. I am doing nothing here in between, because during this time your inductor current is 0. So I can utilize this and deliver current to the other guy, because inductor is resting during this time. So I can do like this. And make this guy high load 1. This will become just shifting it just to make sure. I mean, because they could be different also, not same. So, which means if I know I want PWM like this, then okay. So we have S1 and S2 switches. So during this time, S1 on, off, okay, and S2 will be off here. So depending upon how much time you have, how much basically the high Z time where inductor is resting, you can insert that many output, and that will depend on the load current. If I keep supplying, if let's say I increase the load current of this guy, then my high Z time will reduce. I know that in the DCM, we keep increasing the off time, then load current reduces. So for the light load, very light load, you can even supply 4 or 5 outputs. So that will basically, it will be based on, or you are forced to reduce the frequency. So there are two ways. If I want to cater to more loads, then I can operate at a lower frequency and insert more outputs there. So for the DCM, and this is possible in CCM also actually, but there are some issues with the cross regulation and all those, because inductor current is continuous. So for some portion you are supplying to the other guy, some portion you are supplying to this guy. So inductor current never goes zero there. So cross regulation may happen, but in this case, so this is more feasible with the DCM operation, or when you are supplying lower current. So let's say with one inductor, instead of doing a, let's say 100 milliamp, 4 or 5 different converters, I can just use one inductor and just have a 4 or 5 outputs from there, because inductor can easily handle up to 400, 500 milliamp without any issue. But when you operate in continuous, let's say I want to do a 5 outputs with 1 amp each. So the 5 amp has to come from the inductor only. See, inductor requirement will increase the current requirement. So instead of having a 1 amp inductor, you require a single inductor with a 5 amp. So that inductor size will be bigger actually. So it doesn't benefit much there. But when you operate in DCM, the benefit is more with the, and that's why you will hardly find any product single inductor multiple output which always operates in continuous or caters to high load current. But that is not very successful in terms of efficiency or cost. But we know that by default the inductor is resting when we go in DCM. We try to utilize that to supply the current to more outputs, and you can generate different outputs. And the control is not difficult here, it's very simple. Let me see if I have any. Okay, so it's a type 1 actually. You can see only integrator in the loop, and those two switches are S1, S2, which I had in the notes. I have put a different load current just to show you that it can derive different load currents also and still regulate the output. So this is your non-synchronous. Okay, because I have only diode at the bottom. The reason I have a non-synchronous, I don't need to build a control to turn on the bottom FET. So just to simplify the control loop, I just did like this. And this is generating your control signal, mode 1 and mode 2. This guy actually, the switch control, S1, S2. And you can see mode 1 is, mode 2 is driving these two switches. So let's see. Let me remove this one first. So 3.6 volt and output I am regulating at 1.5 and 1.2. Since it's in DCM, it may take a little bit long to set it. Looks like it is settled. So by the way, there will be discontinuity and you're turning off the switch. So during the time during which the switches are off, the low current will be supplied by the capacitor. That's why ripple will be a little bit higher here compared to standard buck. So this is 1.5 volt on an average, and this is 1.2 volt. Okay, so they are regulated. Now let's see how the current looks like. So in one cycle, the current should be same as 100 milliamp corresponding, and other cycle it should be 50 milliamp. So this one has a less current, so one cycle you will see the peak current will be less compared to the other cycle, and you will see the difference here. See, inductor current. So this is during this time you are turning on one switch, during this time you are turning on the other switch, and that's why you see this difference. And your switch duty cycle, this will also different from for this side. You can see the on time is different compared to this one. Okay. And you can still, I mean, you have a looks see during this portion inductor is still resting, so you can insert one more output here or increase the load current basically. So this will automatically increase, so it will reduce the IC time. Okay, so this you can do with boost also. With boost is even simpler because you know the boost switch is at the output, so you just connect one more switch in parallel, you are done. So number of switches required in the boost will be less compared to what you need in the buck. Here each output requires a switch. There in any case you have a one switch at the output, so that will be go to, and in parallel with that connect another switch, take another output. So all the switches will be connected in parallel. And one switch for the charging the inductor, which connects the inductor to ground. That will be common to all. Okay. So for the boost, it will be like this. Let's say see the boost. So this is your single output. All I need to do. So this is your PWM. That's it. So this will charge and supply current to S1, and second cycle you divert the charge. Okay, any questions?
Sorry?
CCM,
Yeah.
we have two outputs.
Yes.
Then for one cycle, inductor will respond to first PW and vice versa. So won't the other switch will go completely unregulated for one cycle?
It won't go unregulated. Your duty cycle will modify accordingly actually. This switch time, I mean, it won't. What you are doing actually in that case, that's why I said it's when you in the CCM this CDO or CMO operation is not easy actually. When I say cross regulation, that's what it means. Cross regulation means one output tries to disturb the other output and it will never regulate actually. It will go out of regulation. So you have to take care of, and that is taken care by usually making sure that whatever current is supplied here, you have to supply that and here. So I mean that balance you have to maintain. If there is an extra current, you have to throw by adding a freewheeling switch here actually. Okay. So discontinuity is always there. Huh? You cannot say that V out equal to D minus V in formula is gone here completely because of these switches. So now you have to just maintain the inductor average inductor current in each phase is same what is required by the load. And if that is getting disturbed, then extra current you have to throw out by adding a freewheeling switch. So that's why you need another third control or third time duration, which will avoid the cross regulation and you short the inductor. And in that case, you are basically intentionally making the inductor current zero during that time. In that case. So if it doesn't balance out, if balanced out, then you are fine. But that won't be in all the cases. There might be cases where it may not balance out. So the control is not simple there. Cross regulation is the main problem with that, and that's why it's not very successful in the CCM. In DCM, it's very simple because you know you're not disturbing because inductor current goes zero only. Then you operate the other output, so they will not disturb each other. And another possibility could be operating at a boundary of CCM DCM. So in that case, inductor current is continuous. You can say. So what you do, you trigger the other phase only when inductor goes to zero. So CDO at boundary of CCM DC. So this is your IL. It is going like this. You wait until it goes zero. See, this is zero. And that is some load current peak depending upon the load. This is not I load 2. See, if I ensure that my I load 2 always starts when this goes to 0 and remains until here. Now the inductor current will be simply I load 1 plus I load 2. So what you will see something like this. I mean, the shape may not be perfect, but you just get an idea that it will go to 0 and it will be whatever the peak current. So there is no time during which you have a high Z region. So inductor is not resting. So as soon as inductor reaches 0, you trigger the other phase. But the problem with this is frequency will vary. When the load current changes, so the slope will basically, when input output is changing, your slope will change. So it may reach the 0 point at different time. Okay, or if your load current changing, the same may also happen. So in order to maintain this continuity, you have to change the frequency. So if you are not concerned about the switching frequency, then it's fine and you can always keep inductor current continuous. Okay. So it's similar to like you can say controlled on time or like constant on time we were talking about. So as soon as it goes 0, you trigger the next phase, and that will be coming from your control. Okay, the on time will be decided by your V control. Say you're comparing a RAM with the V control, that will generate the on time. So that on time will vary, but it will get basically triggered always at a 0 current information. That's it. And since this 0 is current information will be different, I mean will be coming at different time depending upon input, output and load current. So your on time will get adjusted according to that. That's it. So your frequency will vary. Okay.